What if I told you our galaxy is on a collision course with another? The countdown to cosmic chaos has already begun. Here's what you need to know. What they found was clear. Andromeda isn't just drifting near us. It's locked on a direct collision course with the Milky Way. Both galaxies are moving toward each other at incredible speeds. Andromeda is moving at about 110 kilometers per second toward us, while the Milky Way, including our entire local group of galaxies, drifts toward Andromeda at nearly 300 kilometers per second. Together, that means the gap between us is closing at roughly 500 kilometers per second. Even so, space is vast. Andromeda is around 2.5 million light-years away. That's about 24 quintillion kilometers. So, despite the high speeds, this collision won't happen anytime soon. Scientists estimate that in about 4 to 5 billion years, the two galaxies will finally meet. You might imagine this as a huge crash stars smashing into each other in a chaotic explosion. But that's not quite right. Galaxies are mostly empty space. Stars are incredibly far apart, so most will simply drift past each other like ships in the night. A few stars might collide, especially near the crowded centers of the galaxies, but for the most part, the stars won't crash directly. Instead, gravity will do the real work. The galaxies will pull and stretch each other, creating long tidal tails of stars and warping the spiral arms. Their cores will get closer and closer until they merge into one larger, messier galaxy. This merger isn't sudden. It takes about 1 to 2 billion years to fully settle into a new shape, a massive elliptical galaxy named Milky Way. Our Sun, assuming it still exists by then, will find itself in a new, more erratic orbit, no longer in a neat spiral arm. But the collision with Andromeda is just one part of a bigger cosmic story. The Milky Way, Andromeda, and hundreds of other galaxies are all part of the local group, a collection of about 80 galaxies spanning roughly 10 million light-years. This group itself belongs to the larger Virgo cluster, which contains over 10 galaxies and sits about 65 million light-years away. Gravity pulls our local group toward the center of the Virgo cluster at about 600 kilometers per second. Zooming out even further, clusters of galaxies group into superclusters, the largest known structures in the universe. Our own supercluster is called Laniakea, which means immense heaven in Hawaiian. It stretches over 500 million light-years and includes around 100 galaxies, connecting multiple clusters in a vast cosmic web. But how do astronomers know all this? How can they tell where galaxies are moving and how fast? It's not easy. They combine many techniques like measuring galaxy brightness, rotation speeds, and redshifts the way light stretches as objects move away from us. One key method is the Tully-Fisher relation, which links a spiral galaxy's brightness to its rotation speed, helping determine distances. By comparing distances with redshifts, scientists calculate peculiar velocities, the actual motion of galaxies relative to the general expansion of the universe. Large projects like cosmic flows have mapped the 3D velocities of thousands of galaxies. What they revealed is surprising. Galaxies aren't just drifting apart evenly, they're flowing toward a mysterious region called the Great Attractor. This attractor lies hidden behind the dense dust of the Milky Way, blocking direct view. But its gravity pulls clusters of galaxies, including our local group, toward it at hundreds of kilometers per second. Alongside this pull is something called the dipole repeller, a vast cosmic void with very little matter. Unlike massive clusters that pull galaxies in, these voids allow galaxies to drift away more easily. Together, the Great Attractor and dipole repeller create a cosmic tug-of-war, shaping the motions of galaxies across millions of light-years. Stepping back even more, the entire universe is expanding and accelerating. In the late 1990s, scientists studying distant exploding stars known as Type Ia supernovae made a shocking discovery. Instead of slowing down, the universe's expansion was speeding up. This unexpected acceleration is driven by a mysterious force called dark energy, which makes up about 70% of the universe's total energy. Dark energy acts like a repulsive force, pushing galaxies apart faster over time. We don't know what dark energy really is. It might be the energy of empty space itself, but when scientists calculate how much vacuum energy should exist, the numbers don't add up. Theoretical predictions overshoot observations by an unfathomable amount. Still, dark energy shapes the fate of the cosmos. If dark energy keeps accelerating expansion indefinitely, it could lead to a scenario called the Big Rip. In this extreme future, gravity would weaken so much that galaxies, stars, planets, and even atoms would be torn apart as space stretches faster and faster. But there are other possibilities. If dark energy weakens or changes, gravity might eventually slow expansion and pull everything back, leading to a big crunch, a collapse of the universe back into a hot, dense state. Or dark energy could remain constant, causing a big freeze, where galaxies drift so far apart that stars burn out and the universe grows cold and dark over trillions of years. No one knows for sure which ending will come, but studying dark energy is one of the greatest challenges in science today. So, from the collision of galaxies millions of light years away to the invisible forces shaping the universe's ultimate fate, the cosmos is a vast and mysterious place full of surprises.